The 21-year campaign looks the slide. Have you ever wondered what the North Star for the blast furnace longevity look like? Here is the thing. We are looking at a campaign that didn't just last, it dominated. On the screen you see a dark, moody background with a brilliant glowing orange light at the bottom, like the sunrise of a tapping operation. 78 million tons, that's the figure we are chasing today. So what's the most furnaces are lucky to hit 15 years, hitting 21 years means we have mastered the physics of vessel. So let's look at the life story of this furnace. Three phases of sustained historic output. Question is there, how do you stay productive for the 2 decades without a burnout? So look at this chart. It's a pulse check of the furnace life with a white line for production and a vibrant orange line for the productivity. We see three distinct life chapters bracketed at the top: the commissioning climb, the economic boom years, and finally the prolongation phase, that is the slowdown. You'll notice some deep dips, especially that massive drop in 2009, which represent the global economic crisis. So what? Even after that 2009 heart attack, the furnace recovered and kept running for another 6 years. That recovery is only possible if your internal variables are perfectly balanced. That is the main message. Mastering the variable of the extreme longevity. How do we keep a giant like this alive? It's not one thing, it's an ecosystem. This diagram looks like high-tech circuit board with a neon blue and orange lines flowing into a central vessel at the bottom. On the left, we have defenses, cooling and refractory quality, which are very important. On the right, we have stressor, charge material, processes, operation. So what? Longevity is not a passive result, it's an active tug of war where you use wear monitoring to make sure your defenses always stay one step ahead of the mechanical stresses. So this balance starts with what you feed the furnace. Coming to the stable chemistry, which requires a rigid raw material baseline. Here is the thing, you cannot have a stable output if you have a trash diet. On the left, look at the ferrous burden graph. It's a chaotic ore and purple mount range. But notice that blue bracket at the top, it was logged at 1000 kg per ton. On the right, the coke quality CSR trend is beautiful, a steady climb from 97 to 2015. This systematically replaced domestic coal with a high CSR Australian and Canadian coking coal. So what? By making raw material boring and predictable, the chemical reaction inside stays stable, which protect the lining from the erratic temperature spikes. Coming to the defending hearth with a 12-degree refractory uh, sump. So we have stabilized the diet now. How do we protect the bowl at the bottom? So on the left is a blueprint showing a 12-degree tilt in the hearth bottom. That's the sum. On the right, we see the actual bricks. Japanese super micropore carbon brick that act like a sacrificial anode, and a ceramic cup made of fused corundum. So why 12 degree? It's like the drain in your shower. So what? This angle prevent the dead man from the floating and causing liquid iron to swirl around the wall, which is number one cause of hearth failure. 300 gigajoule per hour of closed cycle thermal shielding. Here is the thing, it's 1500 degrees inside and we need to keep the steel shell cool enough to touch. Look at the blueprint on the left. It shows four distinct cooling circuits using boiler feed water. The photos on the right shows the double chamber copper steps that were a worldwide fast. They took away 300 gigajoule of it every hour. So what? That's enough energy to heat a small town. But here it's being used as a thermal shield to ensure the refractories stay frozen and intact. But even the best cooling need a smart tapping strategy and having the trapping uh, frequency. Question rises that if you want to live longer, do you run 100 sprints or one long marathon? Look at this before versus after table. In 1993, they were doing 15 taps a day. By 2014, they cut that a half to just 7 taps. Tafel faced life and from a measly 3 month to 2 whole year. So what? Every time you open a tap hole, you are stressing the furnace. By slowing down the heartbeat of the furnace, they reduce the thermal shock and triple the life of the cast house equipment. Now coming to the next slide, which is on the evacuating the vessels, the 1728 ton salamander tap. Now let's talk about the grand finale. When the 21-year were up, they had to empty the liquid leftover or the salamander. On the left, you see a 3D model with a blue arrow routing the liquid into three separate paths. The photo on the right shows the crew standing over a river of molten iron, 1728 tons of it. So what? Most plants struggle with a few hundred tons, draining nearly 2000 tons in one go required surgical precision to ensure the hearth is bone dry for the rebuild. Now coming to the raking part, the dry raking, which preserve the carbon foundation. Here the thing that saved them millions. They didn't use a drop of water to cool the furnace down for the rebuild. So look at the before photo with a pile of grey block, then the after photo on the right with a clean dark ball. They evacuated 2200 tons of material using dry raking. So what? By avoiding water, they didn't damage the existing carbon block layers. They were able to reuse that foundation for next campaign, saving months of construction time and massive capital cost also. Coming to the 91-day sprint. So the furnace is empty, the foundation is saved. Now how fast can we be rebuilt? So look at this blueprint. It's a color coded into a 6 horizontal levels. They used parallel architecture, meaning teams were worked on top, middle and bottom all at once, separated by silt safety platforms. So what? They managed to swap out the entire refractory and cooling system in exactly 91 days using 1100 people. It's like doing a full engine swap while the car is still rolling. So coming to the postmortem, reality matches the calculation. This is aha moment for the engineers. On the left you see the pink and yellow theoretical weird drawing from 1993. On right the actual 2014 photo with a neon blue line tracing the weir. They matched almost perfectly. They found that only 1.5 of the three protective layers were actually worn. So what? This proves that their line physics worked. The theory survived 21 years of reality, which is the ultimate validation for an engineer. Coming to our next slide, which is on the decades of residual life discovered. Here, the most surprising part they could have kept going. Look at these photos. On the left, we still have a 350 mm of brick thickness left. On the right, those original copper strips in the bailey were 100% intact. Zero jacket cracks in 21 years. So what? This means the furnace were just limping to the finish line. It had residual life left. It confirmed that 300 gigajoule per hour cooling system we saw earlier was exactly the right shield for the job. Now coming to the engineer campaign. Uh, so designing for the next 20 years, how do we take the great and make it legendary for the next 20 years? This timeline shows the upgrade. We are boosting refractory strength to a massive 280 MPa and widening the sidewall to 600 mm. The final message is at the bottom. Campaign 1 proved the physics, campaign 2 scaled the metallurgy. So what? We are not guessing anymore. We have 21 years of data to build a furnace that might just last for 30.